Okay, so the second talk of this session is GPU-assisted brute force cryptanalysis of GPRS, GSM, RFID, and Tetra. And the talk is given by Jihazir Tezkan. Please, thank you.
Thank you so much. This is a joint work with Gregor Lander. So in this work, I will talk about some GPU optimizations of some block ciphers and stream ciphers like Kasumi Spec and T3, and I will try to explain how practical or impractical it is to break GPRS, GSM, RFID, and Tetra communications. So let me start with a brief introduction. So GPUs are super useful when you optimize symmetric cryptographic algorithms because the parallel computing power of GPUs can be used to optimize symmetric key encryption algorithms, for instance, to obtain fast encryption. For instance, we have the best AES optimization. So on a single GPU, we can encrypt in the counter mode like 4.5 terabits per second, which is super nice, I guess. And your memory or hard disk read and write speed is not that fast anyway, so it is practically free. Also, you can perform brute force attacks on short keys. This is also important. Aryan Lanstra did it on PlayStations, more than 200 PlayStations a decade ago. And some French scientists continue this work. But when you don't do it for the symmetric crypto, people think that 80-bit key block ciphers are still secure or they give you years of security. We still receive from some journals publications where people design block ciphers with 64-bit keys or 80-bit keys, and we have many ISO standards with 80-bit keys, so we are trying to show that it is not secure anymore. Also, verifying theoretical results in practice is super good with this GPU optimization because whenever you get a distinguisher or something, maybe you need to verify it and you need to perform 2 to the 50 or 2 to the 60 encryptions. We can reach that with this a few GPUs in a few days. So let me give you some of the GPU specifications we use. I generally run it on all of my laptops and desktops to show that it is not, the optimization is not specific for a special GPU. So as you can see, only 2 of them are in italic, like RTX 39, because we don't have it, but we will compare our result with from a literature. So people who obtain a good customer optimization for that GPU, we achieve the same with RTX 2070 Super, which is like, you know, the RTX 3090 has like 4 times more cores. So just to show you that how fast the optimizations can get. Also, the RTX 5090 is recently announced, so we don't have it. I just wanted to show you how the next generation actually comes with more GPUs and etc. So compute capability is a little bit important. It tells you the software and hardware features of the GPU, but they are backward compatible. So if you buy the newest GPU, but you compiled it years ago for compute capability, for instance, 5.0, that also runs on the new GPU. So everything is backward compatible. So I will come to this, but main point is that we have tens of thousands of cores. They are not as powerful as CPU cores, but they are still powerful. So you can optimize or implement a symmetric key encryption algorithm on a GPU in different ways. The best way, I mean, the most basic way is the straightforward approach. In this case, you implement all of the steps one by one. But here the bottleneck comes from the number of instructions because you so in this case, every thread on the GPU performs a single encryption. And if the number of instructions are high, so it takes some time. Another approach is the table-based implementation in AES. This is a good thing to do. So if you can divide the cipher or into subspaces, then you can pre-compute everything in a table. Then one round of encryption turns into looking at the tables and XORing the results. And if you keep these tables in the shared memory of the GPU, then you get the best speed. But GPU threads work in warps, which are 32 threads, and all of the threads has a single lane to read this from the shared memory. If they use the same shared memory, then this causes a bank memory conflict. So in AES, we overcome this, and this is why we achieved a very fast speed in the past. Another approach is the bit-sliced method. So instead of working on bits of large words, we can store each bit in a different register so that we can avoid operations that try to access and use bits of words, because some hardware-oriented ciphers becomes harder to implement on GPU. And there are 2 methods to do it: thread level bit slicing. In this case, different threads keep the bit value, but this introduces memory or read-write operations, which causes the bottleneck. Another way is to keep everything in the same thread in different registers, but if you use more than 64 32-bit registers, you actually lose occupancy and things get a little bit slow. So we tried all of these in the following optimization, so I will simply mention the results. So first we started with spec. This is designed by NSA, so we fear that there might be a backdoor. So far we haven't found it, but as you can see, it supports key sizes from 64 to 256. Maybe this is the backdoor, because if you provide a 64-bit version, everybody will use it. And this is the run function. So we actually focused on 64, 72, and 96-bit versions mostly. And I will list some of the optimizations just to show that people what can you do. For instance, we optimized our code with compute capability 5.2. Instead, our GPU is better in compute capability, because people think that newer is better, but people who did mining, who implemented mining algorithms for alternative cryptocurrencies, they always use a previous version to see if it is faster. And here we obtain better speeds just by doing this. So we wondered if we go even further back, if we get speed up. But new CUDA SDKs doesn't support it. So you install older versions, but it didn't work. So although spec 64 and 72 has smaller numbers, we obtain better speeds for spec 9629. Those second numbers is the number of runs. This is because GPU works, the rotation operations are a lot faster on GPU architecture. And also you need to use AND operations if you keep these 16 or 24-bit values on a 32-bit register. So we also use, we unrolled some for loops. But at the end, we could run our GPU kernels with blocks of 1024 threads. Generally, this means that we use a small number of registers in our implementation. So let me come back to the results. So on many different GPUs, these are the results. But if you look at the bottom row, that is the best GPU we have currently. And as you can see, we reach 2 to the 36, almost 2 to the 37 key tries per second, which is for me a super fast. And if you try to brute force, for instance, spec 64, on a 9G, if you use 9 GPUs, it will take a year, which is super practical. If you attack spec 72, which has 72-bit keys, it takes around 1,500 GPUs to break it in a year. But 96-bit version is an RFID standard. Although people prevented it to be an ISO standard for lightweight crypto or block ciphers, somehow it became an RFID standard. Nobody noticed, but you need 22 billion GPUs to break it in a year. And this is not practical, of course. But for instance, if you buy the new GPUs, instead of 4,090, if you use 5,090, that number reduces to 17 million. I'm just trying to, billion, sorry. So I'm trying to show you that in the case of post-quantum crypto arguments, maybe around 2050, this will be practical, because GPUs are always getting better. And if you optimize it somehow a little bit better, or the GPUs come with better properties, we can break it faster. So let me move on to Tetra. So yesterday we had a talk about this, so you know the idea. This is a European standard for truncate radio, and it is globally used by military, police, emergency, prisons, government agencies, and it was recently reverse engineered at Usenix, and this is the picture. So at the top, there is a key register of 80 bits, so it uses 80-bit secret key, and in the below, there is a 64-bit state register. So initially, we tried to do the straightforward implementation, but this didn't provide good results. Actually, I reached 2 to the 27 key tries per second, so I thought that this is not possible. It's not getting anywhere. Then I tried to bit-slice implementation, but this time the key register part becomes harder, and it didn't also provide a good result. Then I realized that maybe I can combine both. So if I go back, for the key register part, I use straightforward implementation, because if you do bit slice, since it is 80-bit, you have to use 80 registers, which takes a lot of registers, and you use the occupancy of the GPU. So instead, we kept the top part as in 2 registers and did the SBox operation at the end. You have to send the SBox result 8 bits to the below part. But we implemented the below part in bit slice version. So actually you do a matrix transposition, etc. So the codes are available. If you're interested, you can see the results. But at the end, these are the speeds we get. So in order to break T3 in a year, you need to have 1.36 million GPUs. So Meta recently announced that they are going to build a new data center with more than 1.4 million GPUs. So Meta can do it in less than a year. But of course, in that sense, it is practical. But if you use this many GPUs for AI operations, you will earn a lot of money. So nobody will try to break one communication and use this. But again, with the new GPUs like 5090, that number reduces to 1 million. So maybe in the next decades, that number will be like 10,000 GPUs or something. So it is really practical in my opinion. So let me move on to Kasumi. Yes, so it's a face-style cipher. The picture is a little bit complicated, but we have 7-bit and 9-bit SBox operations. So this was very hard to do it in bit slice or table-based. So this is, again, I used straightforward implementation. So we start with, storing all of these SBox values in the shared memory. Then, I put some GPU costs, but I'm not going to go much into detail. So actually, this introduced some shared memory bank conflicts. But if you remove it, actually, it doesn't provide you a speed up because these SBoxes, the tables are small, like 8 bits or 16 bits compared to the 32 bits of tables that we used in AES. So second thing is that there are some round constants. You can keep them in shared memory. You can assign it to a register, or you can assign it during the code compilation. And we realized that this is the fastest method. And our implementation of Kasumi for time memory trade-off table creation and performing exhaustive key search are different because in an exhaustive search, we rarely perform the encryption of the last round of a face-style cipher because, if you go back, the right part in the ciphertext, actually the left part in the previous round. So you can check it there, and if it is correct, then you can perform the last round. So our speed changes from time memory trade-off to exhaustive search. Anyway, we kind of achieved that we can run it. So this is a classical kernel call. So it means that we run this kernel with 2048 blocks, and each block has 1024 threads. So this means that with this call, actually, it performs 2 to the 21 encryptions in a single call. But in order to do that, in our key search optimizations, the compiler actually used more than 64 registers, which it shouldn't. So in order to overcome this, we know that it could do it with less. So during the compilation, you have to write this max register count 64 so that the code actually forces it to use at most 64 registers, etc. But this actually provided a 10% speed up. So long story short, we actually tried many stuff and to obtain the best results. So these are the fastest speeds we get. So again, if you look at the bottom row, with RTX 4090, if you use this code for time memory trade-off table creation, you can perform 2 to the 35.56 encryptions per second. But in a key trial attack, it is a lot slightly better, let's say. So why do we do this? Because Kasumi used in 3G with 128-bit keys, but previously in 2G, we were using A5-1. And you can easily create time memory trade-off tables for it because it uses a 64-bit key, 22-bit frame, which is IV. But the internal state of the stream cipher was 64-bit, so you could create the time memory trade-off tables for that. But with the introduction of 3G, Kasumi is introduced for 2G communications, but for backward compatibility, actually it uses a 64-bit key. So a 64-bit key concatenated with itself to form a 128-bit key for GSM or GPRS communications. So there was recently time memory trade-off attacks, which actually provided for this algorithm A53. And for GPRS, these time memory trade-off attacks are possible when the network is misconfigured. This means that the IV is somehow fixed like 0 or something. So they achieved 2 to the 32, that's 72 customer encryptions per second on an RTX 3090. But if I go back, you can see that we achieved like maybe 15 or 16 times faster speeds here. This is important because this actually changes how practical the attack is. So for instance, they said that for the time memory trade-off attack, in the first scenario, they said that if you have 600 GPUs and run it for 289 days, record the results on a 100 terabyte SSDs, you can break a GPRS communication with 0.25 probability if it is misconfigured. Otherwise, you cannot do it. And if the call is long enough, like 30 minutes, your success probability is 0.04, which is pretty small. But with our optimization now, instead of 600 GPUs, you can do it with 36 GPUs, or if you already have 600 GPUs, instead of running it for almost 300 days, you can run it for 17 days. So I'm trying to show you how practical things get if you do these optimizations. So you can use anything in the middle, like between 36 GPUs to 600 GPUs. So let's focus on the scenario 3. So they say that if you have 2,400 GPUs, or if you rent them, it will take 348 days to create the tables. But the thing is that still the success probability is 0.11. So it is low. If the phone call is 1 hour, the success probability increases to 0.21. So it is still not that practical. I mean, you should be lucky to break it. So we said that if we already improved the algorithm this much, why we rely on time memory trade-off? I mean, can't we just do the brute force attack? So also recall that our brute force implementation is faster because we rarely run the last one. So using our optimized code for brute force cryptanalysis of a GSM communication instead of a time memory trade-off attack, we get the following advantages when the scenario 3 with the 1 hour call is considered. I don't consider longer calls because in most countries you cannot actually talk longer. At the 1 hour, it actually disconnects you. So if you use brute force instead of time memory trade-off, your success probability increases to 100%. Instead of requiring to capture a 1 hour communication, communications of any length can be cryptanalyzed. The pre-computation for 348 days is no longer required, and you don't need to store the tables in 200 terabytes of SSD storage. And they ran the online attack on 10 servers with 128 CPU cores. This is no longer needed. And with our optimization, actually, you can break any GSM communication in 38 hours with this many, 2,400 GPUs with RTX 4090. And with the new GPUs, this actually reduces to like maybe 30 hours or less. Of course, this is the worst case scenario. In practice, you get in 20 hours, you can break it. So instead of dealing with the time memory trade-off, I'm not recommending it, but if you want to do it, you can do the brute force attack instead. And if you have tens of thousands of GPUs, you can reduce this attack to minutes. This is problematic because if you can reduce to less than 1 minute, you can break the two-factor authentication during SMS communications because you can get the SMS code and use it for two-factor authentication. We are just trying to show you how practical things can get. With more GPUs, with better GPUs, you can easily do this attack. So people don't share their GPU codes. So in the past, we also did some optimizations. I tried to compare all of the stuff we did so far. So this is important also because in the crypto paper, they didn't share their code. So I don't know why we get 16 times speed up. I contacted the authors and they said that they don't claim that they have the best optimization. But if you share the code, then we can actually, see or improve and use it in future research. For instance, for T3, you can use our codes to see if you can find a weakness in the cipher, etc. So as a conclusion, we showed that we can easily break any GPRS or GSM communications. Breaking Tetra communications will be practical in the next decade. And since these are hardware, maybe they should stop building right now. And breaking RFID communications might be practical maybe around 2050, or if you are optimistic like post-quantum people, next decade, let's say. And all of our optimizations are publicly available, so you can use them. If you improve them, let us know so that we can get better speeds, etc. So thank you for your attention.
Thank you very much for the very nice talk. Are there any questions in the room? There's one there.
Thank you for the talk. Have you considered, in the case of Tetra, the recent results that were shown earlier in this conference that show that you could rewrite Tetra slightly differently, so you may have an advantage when you implement it for key recovery?
Thank you so much. Actually, they asked me how fast I can do it on GPUs. I gave them results, but I didn't have their results. So during talk yesterday, I was thinking the same thing. So what they did is they actually divided the top register into two registers, like 40 bits. The problem is that GPUs work very good on 32 bits, but 40 bit, I have to still use it a larger register. But if they could divide it into 32-bit, and a 16-bit, it will be fantastic, and I will get fantastic speed up. So yes, but of course, maybe they can come up with a similar solution. So this was a very strange implementation for me. For the first time, I did this stuff, doing the bit slice and straightforward combination. So there may be future improvements, and we can. And those improvements sometimes is not like small. You can get like 10 times speed up, etc. So that can change everything. Yes. Thank you.
Thank you very much.
Thanks a lot.
Thanks. Any more questions in the room? Yes, there are two questions here. Thank you.
Thank you for the talk. You gave us results in keys per second.
Yes.
I would be very curious how much power you consume. So results in, I don't know, keys per gigawatt or so.
Yes.
Have you any idea?
The thing is that in this work, I didn't do it, but in our AES work, which we published years ago, we achieved but we were measuring encryption speed there. I think we achieved like 5 gigabits per watt or something. So these GPUs consume around 200 watts per. So you can divide it per watts, but since we do all of the stuff on a single GPU, actually on my desktop at the office, it runs for a few days and get the results. So we didn't worry much about the this power consumption much. Yeah, but you can measure. Yeah, it's not that hard. Also, in our keys per second, we do the key schedule, right? So if you do encryption, you do the key schedule once. So these speeds are actually increases when you do the encryption. So
I would be interested in how much the attacker actually needs to, how much power the attacker is going to spend.
I see. Yeah. For like Tetra attack, I mean, since we are going to run it for 1 year, we should calculate, but it will be much, yes. But again, they always do this for AI computations. But of course, they get a lot of profit, so they don't mind. But yes, a lot of power consumption, yes. So, but if you're a dedicated attacker, you can build ASIC, so it will be faster than these GPU results, since this is the general purpose device.
Thank you.
Thanks. There was another question here, Yevan. Yeah.
Thank you for presentation. So I have a question regarding, so with this speed up, I mean, the number of cycles is the same, and would be in the future the problem with the memory access that, I don't know, after, if we have this many cycles, the memory just died after some number of encryptions.
You mean memory dies, you mean?
I mean the problem that with the hardware that we cannot access memory so much times.
The thing is, GPU miners are using the same GPU almost like for a decade, and the modern GPUs are super powerful. If you don't overclock them, they run for years, so they don't cause hardware problems. So they're a lot easier to configure than an FPGA. So sometimes we run it for months, and the GPUs we bought like 10 years ago still runs, and there's not that much problem. But if you overclock it, you might have some soft errors, which means that some bits might flip in the memory. But generally, since you are doing a key trial, if there's an error in one of your trial, most probably it wasn't the correct key, so it wouldn't affect your result anyway. But of course, you can always turn on ECC, error correcting codes, and this way you can get reliable results, but it introduces a little bit slow though.
Thank you.
Yeah, I think, a bit of a stupid question. Sorry.
Sure.
Sorry. So a few years ago, there were a lot of attacks, by-click attacks. I don't know if you heard about it, that included an exhaustive search on the key, but that computed less part than the whole encryption with some meet-in-the-middle attack ideas. Do you think trying to implement something like that would be better than the brute force attack of the classical?
It depends on the complexity. I don't know if you mentioned the customer, but there are some, for instance, attacks. I mean, the exhaustive search requires 2 to the 64, so there are attacks like 2 to the 61. If you modify the code, of course, since you modified it, introduces a little bit overhead, but still you get a lot of speed up. So in the paper, I mentioned about this customer big attacks, I think, or meet in the middle attack. So yes, you can run it in like 10 hours instead of 38 hours of our brute force, but of course that attack requires to capture more data.
Okay.
Yeah.
Thanks a lot. So let's
Thank you.
Thank you very much. Let's
Thank
the speaker again, please.